My name's Frank. I'll be your moderator here this afternoon for this technical session put on by Andrew Ginter, and Andrew's from Waterfall Security Solutions. Andrew is the VP of Industrial Security and Waterfall at Waterfall Security Solutions. Andrew's team works with a lot of the most secure industrial sites on the planet. He is the co-chair of the ISA's SP99 working group. I'm going to get him to explain that one, the acronym for that, when he comes on board here. And author of 2 industrial security books, which is at the back if you want to have a look. Both of which are available at the back, as I just mentioned. He spent 20 years developing SCADA systems, products, and another nearly 20 years on industrial control system security products. So please welcome Andrew.
Thank you, and thank you all for the opportunity to chat with you. A word about the ISA. It's the International Society for Automation. Their SP99 working group is a working group of volunteers that are producing industrial cybersecurity standards. They actually have, I think, 14 working groups. I'm the co-chair of one of them, working group number 1. And they produce the world's most detailed industrial cybersecurity standards. The International Electrotechnical Commission, IEC, headquartered over in Europe, but with international participation, every country has delegates to the commission, has adopted the ISA SP99 security standards as their 62443 series of cybersecurity standards. At this point, the volunteers at the ISA produce the standards, and the IEC publishes them as the 62443 series. I'm going to talk about cybersecurity. I am the author of 2 books on the topic. There a number of copies of them all are at the back. You're welcome to take some with you. The red book is more introductory. The black book is more advanced. I assume that you know everything in the red book and then some. I would encourage you please to take one each, and if there's leftovers at the end and you want to get the second one, or you have a colleague who you think would benefit from a second copy, go for it. So let's get started. The essence of industrial cybersecurity. I mean, a lot of people are familiar with basic cybersecurity, keep our credit card numbers safe, this kind of thing. At industrial sites, the priorities are different. The first priority at every industrial site I've ever had the privilege of visiting is safety. Don't kill any of the workers. Okay? Don't cause a public safety catastrophe. Don't make our populations ill. Don't issue a boil water order. And the number 2 priority at every industrial site I've had the privilege of visiting is reliability, which means keep the process running, keep fresh water coming out of the freshwater treatment system, keep treated water coming out of the wastewater treatment system, continuous, correct, efficient operations. And one important aspect of that is that some of the very nastiest of cyber attacks are actually able to physically damage our equipment, the equipment we use to treat water and refine petroleum and everything else. And it's one thing to suffer downtime for a few hours and come back up and everything is good. It's completely something else to physically destroy one of the pumps that we use or some other piece of physical equipment, and now we're down for weeks, if not months, before we can come back to full production. Safety first, reliability second. Cybersecurity is essential to safety. In the modern world, everything is automated. Without security, we have no safety, we have no reliability. This is the point. Who in the audience here is from IT? Okay, you guys know this world better than I do, so I had a couple of slides of, there was one? Okay. I'll say a couple of words, but you folks know control systems and SCADA systems. This is the control room at what was Detroit Water and Sewerage. It may now be the Great Lakes Water Treatment Region. The city of Detroit went bankrupt and there were changes of names and changes of ownership. But when this photo was taken, this is a customer of Waterfalls. one operator sat here, 24/7, controlling drinking water treatment for 2.5 million people and wastewater treatment for 7 million. A lot of the surrounding communities sent the wastewater to this facility, or there's actually 5 facilities up here for treatment. One supervisor looks over their shoulder. When the operator goes on break, the supervisor sits down. Continuous human supervision. The technology that you see here, all of it very roughly together, is called the human-machine interface. You know, those of you who work with this all day long know that some of these are alarm servers, some of them are GIS systems, but sort of the all-encompassing name is human-machine interface. It lets us visualize and manage hundreds of thousands of measurements and control points. A typical system that I see at our customers, I don't know how many Detroit Water has, but a typical system is somewhere between 5,000 and 250,000 measurement points, and a smaller number, typically 1,000 to 10 or 20,000 control points. So these screens that you see here, typically between 500 and several thousand screens, you can navigate between them, you can drill down, you can see details. This is part of the cyber system we need to protect. If we impair this, we've lost the ability to supervise whether operations are still working safely. We've lost the ability to control operations. A second class of target in the industrial systems is the physical equipment. This is the computers that are physically connected, electrically connected to the measurement points, to the flow meters, to the actuators, to the controls. So they go by different names. This is an arcane business. A lot of this stuff was invented back at the beginning when computers really couldn't do anything, and they were just barely tricked into doing something useful. And so everything useful that you needed a computer to do had a different name. Nowadays, of course, everything can do everything, but these devices still have names like programmable logic controllers, PLCs, remote terminal units, RTUs, flow meters. The beastie on the bottom there is a pneumatic controller. At a lot of our physical installations, we see compressed air being used to physically move things. The beauty of this is that the controllers can be standardized. It doesn't matter what we're moving. Compressed air is doing it, and the controllers can measure and control the flow of compressed air for anything. Compressed air is compressed air. So with that lightning introduction to industrial systems, we come to security. In the Red Book, I coined the first 3 laws of SCADA security in an effort to basically simplify this. The name of the presentation is both simpler and harder than it seems. Here's part of the simplicity, and by the end of it, we discover some of the difficulty. First 3 laws of SCADA security: nothing is secure. Security is like safety. We can always be safer, we can always be less safe. Are we safe right here, right now? It's a meaningless question. Safety is not a yes or no thing. Same thing for security, it's a continuum. Anyone who uses secure as an adjective, secure communications, secure device, secure boot, secure this, secure that, is selling something. How would I know? I do that. See if you can catch me at it. Second law: all software can be hacked. I produced software for 20 years. I wrote code myself. I led teams who produced code. And in spite of my best efforts, in spite of the best efforts of everyone, all of my colleagues, every piece of software we ever produced had bugs. Some bugs are security holes. Some of them we've discovered, some of them we haven't. Some of them the bad guys have discovered before we do. In practice, all software has bugs. Some bugs are security holes. All software can be hacked. This is part of the problem. We have software controlling everything now. Worse, all cyber attacks are information. This is the definition of cyber. This is what cyber means. And every single bit of information can be an attack. A single bit can be an attack. The bit says, open the valve. That can be exactly the right thing to do right now, and it can be exactly the wrong thing to do 10 seconds from now. Then the bit had better be 0. Close the valve. So put all this together, and what we have is, what's the trend for the last 35 years? Computers get cheaper, which means there's more of them everywhere, controlling everything. Everywhere there's computers, there's software. The more computers we have, the more targets we have for cyber attacks. Second trend for the last 35 years is increased connectivity. Connectivity gets cheaper and more ubiquitous every year that goes by. Connectivity is how we communicate information. Some information is attacks. Trend for 35 years has been more targets and more opportunities to attack them. Anyone wants a career, if you're advising young people nowadays, the security problem is going to continue to get worse as long as these trends continue. It's going to get worse before it gets better. What's the bottom line? If we compromise a computer that is able to control the physical world, control any aspect of the physical world, in the worst case consequence that we have to consider is that that computer, that CPU, will issue every unsafe instruction to the physical world that it's physically able to issue. Do not be deceived by vendors who say, the software will prevent it from blah, blah, blah. If we compromise the software, the CPU is ours. It's running the bad guy's instructions. And we can make that CPU do anything it's physically capable of doing. So this is the hard part. It looks bad for our heroes at this point, but bear with me another couple of slides. It gets worse before it gets better. This is the modern attack pattern. I've talked about all software has bugs. These bugs are called vulnerabilities. Taking advantage of a vulnerability is called an exploit. Exploiting software vulnerabilities is hard. You have to write code to do it. Now, if someone else has written the code, you can just use it. But if you discover your own vulnerabilities and write your own exploits, it's hard. It's not impossible. But the modern attackers, bluntly, are lazy. We're all lazy. If they can find a way in without exploiting vulnerabilities, they'll do it. Here's how they do it. They steal passwords. They use permissions. They steal a password, they log in with their password, their stolen password. They steal more credentials. There's some technical stuff called pass the hash. If a Windows administrator has logged into the Windows machine that they break into with a stolen password, anytime in the recent past, they can use what's called a password hash to gain administrator privileges. They can log into the domain controller and create a new account for themselves. Call it something benign like admin backup-2. Is anyone going to touch that account if they see it appear out of nowhere? They'll go, oh, better not touch that, that's important. Backups are important. They're going to give that account universal permission, and now they can do anything they want to any machine they want. The modern attack exploits permissions before it exploits vulnerabilities. And a lot of us who are not really familiar with the space will ask, well, that's all well and good, but why would I worry? Who wants to attack us? Who hates us enough to attack us? Well, this is described in detail in the Red Book. There's a whole range of people who are happy to attack us. Some of them do it for profit, others do it because they hate us, even others do it for political reasons. On the far end of the spectrum here is what's called the NationState attacks. The truism in cybersecurity is given enough time and money and talent, any security posture can be breached. Remember, nothing is secure. Given enough resources, we're done for. That's the far end of the spectrum. A lot of people say, well, nation states aren't going to come after us. Who hates us? Little town, I come from Brooks, Alberta. Who hates Brooks enough to attack them? Well, is there no nation state with a proven cyber capability who's really mad at Canada right now? Oh wait, yes, they've boycotted all of our agricultural products, and they have a proven cyber capability. Is there no nation state who wants to tamper with our elections by making our elected governments look bad by a whole bunch of boil water advisories? Well, there actually are people tampering with our elections. So, like it or not, we are targets. A lot of us as well will say, that nation state stuff, that's like asking, private industry or the town of Brooks to defend itself against, a military assault by tanks and bombers. The government looks after that. And that's true when we're talking warfare, when we're talking physical warfare. We rely on the government and the military to protect us from the most sophisticated physical attacks. The bad news is this does not work in the cyberspace. The most sophisticated attacks move too fast for governments to respond. Governments might detect them, but how long does it take for them to put people in a car and drive out to our site and help us defend against these attacks? Governments might see some of this in action and spread information about the kind of stuff that might be coming, but in a sense that's backwards looking. That's what people, basically if a site gets breached already, we can spread the information about the breach, and everyone can use the knowledge to protect themselves from future attacks like that one. This is called information sharing. It's a big thing that governments all over the world are doing. Again though, if there's a simultaneous attack on all of us, information sharing won't help us. The government can't respond fast enough. One of the great fallacies of cybersecurity is that we do not need to defend ourselves against the most sophisticated attacks. One of the great simplicities that I'm coming to in another slide is that we can do some very simple things. And if we can slow down those even very sophisticated attacks, two things happen. One is now the government can help us. Two is it doesn't cost us much, and it saves us money on the low end of the spectrum. Most of industrial cybersecurity in this industry, in lots of industries, in this province, in lots of geographies, most of industrial cybersecurity is focused on the low end of the spectrum, which is high frequency, low impact attacks. Okay, somebody in the electric sector tampers with a smart meter and steals $100 worth of power. Big deal. 1 million people do this. Okay, now it's a bigger deal. High frequency. Each of the attacks is low impact. You can model them statistically. You can protect against them with software. You can slow these attacks, that class of attack down acceptably with software. The high end is high impact, low frequency. This is the problem. So let's talk about what can we do, simple measures we can take to address the high impact and discover that these simple measures we've taken are actually taking a big dent out of the low impact. And the beauty of that is that the low impact protections, they're all software, but a lot of the protections are very difficult and costly to apply to industrial systems. They make crystal clear sense on cell phones and consumer devices. They don't work so well on industrial systems. Just one example, if you're curious: security updates, changed software. Install it on all of our systems, and 24 hours later something unusual happens, and half of them blue screen. We can't do that. We have to test the wretched stuff first. The testing process slows down deployment and costs us a lot of effort. What can we do about it? Here's a few things. It's not just me who's writing books in this space. This book came out less than 6 months ago, came out in November of 2019, and it's brilliant, okay? I read the book and I said, look at that. Everything in the book is absolutely obvious. This is absolutely the right way to do it. Security PHA review. PHA is process hazard assessment. Assessment, analysis, something, process hazard, it's a safety thing. I read the book, I said, this is absolutely obvious, and I didn't know any of it until I read the book. It's the best kind of book. It's obvious in hindsight. You read it, you go, why haven't we all been doing this for 20 years? What to do? A process hazard analysis is a safety analysis. Engineers do this all the time. They say you need, hydrogen sulfide protection here. You need, CO2 asphyxiation procedures here. You need. These are the places that you're going to die if you're sloppy about your procedures. And the engineers design mitigations for those safety risks. Security PHA review adds an extra column into the matrix that the engineers use, and it has to do with security. It basically says, look, if your mitigation is software, you've purchased a safety instrumented system to do your hydrogen sulfide detection and raise an alarm so people can run away and not die, that's hackable if it's connected to a network. If it's just sitting there by itself, well, the Russians can't get at it, the Chinese can't get at it, there's no way to get at it. But if it's on a network, it's hackable. So they give some criteria for what's hackable and what's not. And they said, look, if your mitigations are hackable, you've got a problem, you've got to do something. What they recommend, wherever possible, is physical mitigation. So if you have, let's say, an unsafe condition that arises if a tank gets too full, the usual control system mitigation for that risk is program the control system to turn off the motor, the pump, when the tank gets full enough. A physical mitigation would be a little bit higher, add an extra 1 or 3, depending on the amount of redundancy the engineers determine you need, 1 or 3 level switches, so that if you reach that level, in spite of the software, it physically disconnects the power to the pump. And now you can't pump anymore into there. These are physical mitigations for cyber risk. The only way to defeat a physical mitigation is for the bad guys to send one of their people to the physical mitigation and whack on it with a hammer. And this is the kind of thing our governments are very good at protecting us from. This is the kind of attack that we reduce our enemies to if we've deployed physical mitigations. The problem is, and this is not a problem, this is a limitation, this is a great methodology for safety risks. One of the problems is it's difficult to mitigate some safety risks without software nowadays. A second one is that the mitigation generally shuts everything down. Religion in the safety world is if you encounter an unsafe condition, do something to return to a safe condition. And often the way you do that is you shut everything down. Of course, in the industrial space, we don't want to shut everything down, so we want additional layers of cybersecurity, but this one is brilliant. A second layer is what I describe in the Black Book, and a word of, just full disclosure, I did not make this stuff up. Waterfall works with some of the most secure sites on the planet. Most of North America's nuclear generators are our customers. A lot of refineries, a lot of petrochemical pipelines, a lot of the largest water systems, and we're happy to work with all comers. Even some of the smaller systems say, I want this, and we do it. So I've documented what they do. I gave it some consistent terminology because everyone called it something different, but all I did in the Black Book is document what the world's most secure sites do. Here's some of what they do. They ask different questions. They get different answers. They see the world a different way. In the conventional way of looking at cybersecurity, people see the world as protecting the information, protect the confidentiality, the integrity, the availability of information. The sites I work with do not see information as something they need to protect. They see information as the threat. All cyber attacks are information. They seek to protect correct, efficient, continuous physical operation from information, more specifically from attacks that may be embedded in information. How do they do that? They will look at the perimeter. The cyber guys will tell us, the IT guys will tell us the perimeter is dead. Where's the perimeter around this? There is none. But every important industrial site, every important site in our water system has a fence around it, doesn't it? And wherever there's a fence and guards and gates and guns, there better be a cyber perimeter as well, because the bad guys can get in all of these ways. What we see these secure sites doing is taking an inventory of all of the ways that information can enter a control system. The only way a control system can change from an uncompromised to a compromised state is if attack information enters the system through a physical or a cyber perimeter. A complete inventory of information flows is a complete inventory of attack vectors. Deal with those vectors. We've dealt with attacks. There's only 2 ways information can flow. It can flow online, which means nothing moves physically, through the air, through a wire, through a fiber. That's online. Or offline. Offline is where information is physically carried through a perimeter. The offline measures, I'm just going to give you a couple of examples, but this is chapter 4. The offline measures seek to control the flow of information, the movement of information on physical media. So you'll see people with removable media controls. They will glue shut the USB drives. They will physically remove the CD drives from any equipment that does not need it. And whenever we need, whenever there's absolutely no way to avoid carrying something into the control system, we scan it first. Take it to a scanning station that's got 2 or 3 or 6 antivirus systems on it. Scan the media, copy the new files that we need to a new piece of media. It might be a new Write-Once CD or a new USB drive that's never touched a computer on the outside that is a control system USB drive, and copy the clean files there and use them. So seek to control, to discipline the flow of information from the outside world into the control system on USBs, on laptops. If a contractor comes in with a laptop that they were reading the news on a minute ago on the hotel network and are now carrying into our control system, that's a very bad idea. If a contractor needs a laptop inside our control system, let them leave their laptop at the door, open the locked door, go through, pick up the control system laptop on the inside that's got all the software anyone's ever going to need on it. Use that to walk around our server room or our physical process, but you do not carry potentially compromised laptops from the outside in. I'm going to skip a couple because I'm running too late. Let me talk about online. Online communications, people generally rely on firewalls. People imagine I have a firewall, I have crypto, I must be safe. They're mistaken. Let me give you just one example. The low-tech way. What's the easiest way to break a firewall? You all know it. Throw information at it. That's actually a little bit harder. What I was thinking of, but that works. That's in, if you look up my white paper, 13 Ways to Break a Firewall, that's actually number 3. Number 1 was look over the shoulder of someone entering the admin password. Wait till they leave, enter it yourself. Add a rule that says allow all. Okay, it's all over. That's it, low tech. So, firewalls buy us something, but generally not enough to defeat the nastiest of attacks. I work for Waterfall. Full disclosure, Waterfall sells this stuff. This is what we do. We produce unidirectional gateways. The most secure sites on the planet forbid firewalls between control critical networks and the outside world. They use firewalls inside, they use firewalls outside, they forbid them at the boundary. One layer of unidirectional firewalls defeats even the most sophisticated of attacks. The unidirectional gateway, for the record, is physically able to send information in only one direction. There's a fiber optic transmitter on one side, a short piece of fiber, a receiver on the other side. You can send from one to the other, but the receiving hardware has no laser. It's not physically possible to send anything back. And there's a bunch of software involved that provides compatibility. So you can take a firewall out, you can put this in, and everything still works. It's mysterious, but I won't go into detail because I have another 8 slides I want to get through in 3 minutes. But it's all there in both chapter 6. I think it's actually coincidentally chapter 6 in both books, so it'll talk about how to do this. A lot of people will say one way out, nothing back. Even if it is highly compatible, something has to come back. I need antivirus to come back. I need my vendors need to come in. A lot of people will say it can't possibly work for me. Chapter 6 in this book is 20 unidirectional network designs for 20 business needs. The solutions, the unidirectional solutions to these problems of antivirus updates and whatnot, they're counterintuitive. There is a way to do it. It's much more secure than a firewall. Have a look, or catch me afterwards with your favorite scenario, and I'll go through it with you. I did want to say, if you're interested in industrial security, I've got 30 minutes here. Thank you for your attention. If you'd like more detail, we are running a podcast called the Industrial Security Podcast. Go to your favorite podcast app on Android or iPhones. We have a different expert guest every week. It's not about Waterfall. Waterfall sponsors it as a public service. It's about our guest. We have one expert after another showing us their view of the elephant, and there's a lot of views of the elephant. A word about Waterfall. We serve the most secure sites on the planet. We produce a whole family of technology. The flagship is the Unidirectional Gateway. If you would like a consultation so we can look at your network design and give you a proposal, we sell product, not services. Consultations are free. Technical proposals are free. Bring us in for an hour or a half a day. This man up front here can arrange that. We'd be happy to give you our best insights, no charge. The bottom line, the threat environment continues getting nastier. The attack techniques and the attack tools, the software tools the attackers are using just get more powerful every day that goes by. What I document in the Black Book is the practices of the far end of the bell curve. These are the most secure sites on the planet. The problem is that because of the threat environment getting worse, all of us are increasing the strength of our cyber protections. The entire curve is shifting in the direction of where the most secure sites are right now. It seems to me inevitable that the practices of the most secure sites are going to work their way into all of our industrial cybersecurity practices. I encourage you, read whichever part, book it makes sense for you at your learning level, and pick and choose and say which of these approaches, which of these techniques do I want to use now, which of them are going to come later, because I suggest they lie in all of our futures. That's what I had. Thank you so much.
Any questions for any questions for Andrew?
Questions, argument?
Takers?
I'm very grateful no one has tomatoes.
All right, reminder, casino night upstairs, sponsored by Woolsey.